welcome to tonight's Fine Homebuilding webinar, Meeting Current Energy Codes with Continuous Insulation. I'm Rob Watzak, your host. First off, I want to thank Ox Engineered Products for sponsoring this presentation. Ox's Ox-IS sheathing is a 4-in-1 product providing structural sheathing, continuous insulation, and weather and air resistive barriers. And you can go to Ox Engineered Products to learn more. So tonight we've invited building code expert and educator Glenn Mathewson to give an overview of the latest changes to the energy compliance options for building assemblies laid out in the 2021 IECC. And after he goes over that and a little bit of history on those codes, he'll dig a little bit deeper into the building science about why and how these solutions work to make our buildings more energy efficient. Thanks for joining us, Glenn.
Thank you.
And after Glenn's presentation, we're going to have a Q&A session live here, just typing in the Q&A box, the Zoom Q&A box. And for that presentation, we'll also be joined by Lee Bybee, who's an architectural materials expert from Ox Engineered Products. Welcome, Lee.
Thank you.
All right, so I don't want to waste any of Glenn's time. I know he's got a lot to share with us. So take it away, Glenn. We'll see you at the end of your presentation.
All right, here we go. So thanks so much. Again, I'm super excited to get to present this to you guys. Very thankful to Fine Homebuilding and, of course, Ox Engineered Products for sponsoring this education and letting me come here and just share with you what I do, which is teaching building codes. So this is a brand new presentation I put together just for this event, Exterior Insulation and the IRC. This webinar is based on the 2021 International Residential Code, which includes the provisions from the 2021 International Energy Conservation Code. And I'll give some details on that in a little bit. As was already mentioned, it's sponsored by Ox Engineered Products, which again, I'm really thankful for when there's folks that partner with me to help me do what I do, which is just teaching building codes, and that's that. And then it's presented by, of course, yours truly, Glenn Mathewson with buildingcodecollege.com. I only have 45 minutes and some Q&A time with you guys, which is hard for me because I'm used to teaching like full day code classes. So I don't want to spend much time introducing myself. My name's Glenn Mathewson. You can go to glennmathewson.com and you can get my bio and learn more about me. But this is just kind of a collage of stuff. I've been in the construction industry since I started as a laborer at age 19. And look at me now, Mom. So super excited to be here. And let's get going on this. And the first thing I have to clean up is, what are these books? What is this stuff? IRC, IECC. These are simply model codes. They don't have any authority in and of themselves. Now, energy codes are created in this one standalone book, the International Energy Conservation Code. And within that, you have energy conservation provisions for commercial and residential occupancies, like single-family homes, the kind of stuff that would be regulated under the International Residential Code. And the provisions from the IECC that apply to 1- and 2-family dwellings and townhouses, the buildings regulated under the IRC, all of those provisions are simply pulled out of the larger book and put into Chapter 11 of the IRC. So that's kind of how this works. And from this point forward, since this is fine home building, we're dealing with homes, I don't want to complicate things with this larger energy code. So I'll be referencing and showing you sections from Chapter 11 of the IRC. And like I say, these are just model codes. They're developed by the International Code Council. They host the procedure and the process to develop these codes, but it's an open process. Anyone and everyone can be involved with. I've been writing proposals and attending the hearings for over a decade. These model codes are free. You can, if you want to buy the book, if you want to own paper, obviously that's not free, guys. It's paper. But the access to the information is free. You can go to this website, codes.iccsafe.org. And I always like to make sure people know that because, right, we associate codes with government regulation. And, you know, a lot of folks find that to be a negative kind of thing. Oh, I got to pay for these rules. So I like to make sure everyone knows you don't have to pay for it if you just want the information, codes.iccsafe.org. Now, what are model codes? What I call them is basically collective lobbying. ICC hosts a procedure for everyone to get together that wants to participate to say, let's argue this out, let's hash this out, and let's come up with our collective lobbying that we will then recommend to state and local governments. Now, state and local governments, Those codes are different. Those are called government codes. This is the way I refer to it. We got our model codes, collective lobbying, and we say, hey, government, do you want to take this? We think you should adopt these. And governments go, yeah, we don't like this. We don't like that. We want to change this. We want to change that. Same thing that happens in the ICC hearings, right? Human beings with different opinions arguing it out. So governments can obviously, they'll adopt and amend these. And that's where I want to stress to you guys, everything I'm going to teach you today is model code. It's what's being recommended to the state and local governments. You as a local professional, wherever you're working, you should not be looking for me in Colorado to teach you your local laws. You need to stand on your own 2 feet and empower yourself to learn those locally adopted and perhaps amended codes. Just got to really drill that in so everyone knows. All right. So let's get into energy code compliance. First of all, just simply what's the procedure for complying with energy code? And this is going to be a shocking slide to you in a code class. Make your own choices. Like what is it afternoon class? Have I already had my 5 o'clock beer? What's going on? What kind of moron would tell you in a building code regulatory type of education that you get to make your own choices? Well, you do, but you have to learn the information so that you are in a position to even make your own choices. And this is nothing new, guys. I'm going to take you way back in my collection. If you see behind me, there's a lot of history books and stuff, or my camera's probably not on for you guys to see, but I am a historian of building codes as well. That's part of being an educator and consultant is, I kind of got to know the industry, right? So this is a book of mine from the 70s, Residential Energy Conservation. And this is put together by the Congress of the United States. This was right during the 70s, the oil crisis, the energy crisis. And they put together this large research book about, as you can see up at the top here, in one of the sections for construction. And the guidance here will enable the effective use of energy in new building construction. And notice what it says, 3 compliance paths are offered. 3 paths are offered. That's choices, 3 choices already. And this is before we even had energy codes created. This is just the government saying, hey guys, we would like you guys to create some codes that we can look towards. And so we get these 3 methods of compliance. You've got the specified acceptable practice provision. And that simply is about energy loss. That's about R value, minimum R values of individual insulation components, right? R value is restricting the movement of energy through it. And so that's what it was completely focused on. Put enough restriction of energy loss in these individual insulation components. And then the next one was the subsystem approach. And what this allowed you to do was say, all right, well, we can trade off some of these energy restrictors, right? R value. Maybe you use a little less insulation in the walls, but you use a little more insulation in the ceiling. So it was a way to look at it not as individual components, but look at the entire building thermal envelope and do kind of trade-offs between. But both of those systems were all simply focused on not letting the energy get out of the building or get into the building, if in our hot climates, all focused on energy movement. The third system expanded a little further and said, hey, what about energy creation? Because, right, this was all about depletable resources. If we had a world of just like some magical, abundant, free energy, by rubbing your hands together and you can go 1,000 miles on your car, we probably wouldn't be having any of this discussion. We wouldn't have to conserve the energy. So the third approach said, hey, if we can encourage folks to create less energy in the house, then we don't have to worry about restricting the loss of so much energy, right? Because we're creating the energy in a more efficient way. So that extended to systems like mechanical systems, a higher efficiency furnace, a higher efficiency appliances, better heating of or insulating of your water pipes, all kinds of other methods to get to this overall concept of conserving energy. Now, finally, the federal government, with funding and with interest in this, they were able to promote and fund the creation of the model energy code. And this was our first real energy code collective lobbying to then be put out to governments to adopt. And we can see we have those same 3 concepts just under some different titles. So this is the one about minimum R value of your individual components. This is about the overall U value, as it was called then, of the entire building thermal envelope. This allows you to do the trade-offs. And then the third, which was the systems analysis, which is about cost of energy. That's kind of what it came down to, of how are we going to compare this? How are we going to determine energy creation with energy loss? Well, we're going to have you compare to a standard house that's just using the R value or U value approach, just the insulation approach for not losing energy. And that cost of energy method said, all right, take the yearly costs of that base, that standard built house, and now tweak it. Put in higher efficiency furnace, put in different appliances, put in better windows, change it all around. And as long as you don't spend more money than that baseline house, then you comply with code. So we started in the 70s, guys, with 3 different choices. Now, today, 2021, the code lays out these different 5 options here. Really, it's 4 options and then a 5th one we'll talk about briefly. Well, very briefly. So the first option we get here in the 2021 code is called the prescriptive compliance option. And this one is basically this option of the past. It just simply gives you either the maximum or the minimum U factor for the entire thermal envelope, and then you can do things, or excuse me, for the entire assembly. So that way, whether you're 24-inch on center or 12-inch on center or 16-inch on center, doesn't matter. It's all calculated into what is the overall U factor of that assembly. And I'll talk a little bit more about what U factor is in just a minute. And then the other option you have is simply to look at individual component R values, like, you know, the R20 in your walls, R60 in your ceilings, et cetera, et cetera. And so also within the prescriptive path, so really so far I've shown you kind of 2 ways to calculate your energy compliance under the one option. And then you have a third way to do your energy compliance under again, that first prescriptive option. And now what that's called in the code is total UA, but it's the same as what was developed basically, again, in the 1970s. And the total UA approach, this is something you guys may be more familiar with, the term ResCheck. Right? ResCheck is probably something you guys have all heard of. This is a software by the energy.gov, right? The Office of Energy Efficiency and Renewable Energy, basically the federal government's Department of Energy. And they put together this software that's free to download. And this allows you to put in the areas of your different thermal envelopes. And that's where you can do your trade-offs, right? You can do a little more insulation here, a little less insulation here, so that overall the thermal envelope complies. So this is a slide I was going to develop a little more, but I'll just talk through it. I kind of think about it like a peanut butter and jelly sandwich. And imagine you're trying to create a peanut butter and jelly sandwich for someone with a certain amount of calories. And that's like the energy code. The energy code saying, hey, we want this much energy conservation. And in my analogy, I'm saying we want this many calories. Well, the cavity, the R value method may simply say, use this much peanut butter, this much jelly, and this much bread, and you will meet those calories. But the ResCheck methods allows you to have a computer and a software program that says, okay, well, you used thicker bread with higher calories, so we can now use a thinner peanut butter, or, you know, you've added more jelly, so we can do less peanut butter and get you to that same calories. And so these are kind of the choices embedded in here, and just a start of the choices that you have. So those are 3 different ways to approach your energy code compliance, all under that one option, the prescriptive compliance option. Next up, you get what's called the total building performance option. And this is where I don't want you to get thrown off with the words of the old code. You notice there in the bottom left, it says building design by component performance approach. That's not the performance method. The language is kind of changed around. The performance method is now speaking to the original systems analysis, if you will, where again, we're looking at the overall performance of the building, everything energy related. So that includes not just how much energy you're losing or gaining through your thermal envelope, but how much energy are you creating and how much is the cost of that energy. So this allows you to put in, again, higher efficiency appliances, maybe on-site renewable energies. Solar panels, you're not paying for energy, so that can go into all of these calculations. And then another new method came out, and this was not one from the original 1970s. and 1980s model energy code. This is the energy rating index option, and this showed up in the 2015 IRC. We already had a lot of home builders that were using an energy rating systems. You probably heard of like the HERS rating system, where they were using that as an above code method to be able to sell to their homeowners, hey, we have this Energy Star rated house, or all these different programs where we've actually had a third party come in and inspect. Not just did you put in the insulation R value, but did you actually install it in a way that it will be effective? So the energy rater, I call this kind of a verified energy rating process. This is, again, where you're not just saying on paper, hey, I'm going to build it like this and like this, but you're actually having inspectors come in. These are third-party inspectors, and they'll look at what's the actual quality of this installation. And that method is going to point you to this standard that IECC and ResNet put together. And you can see here's the standard for the calculation and labeling of energy performance using an energy rating index. So that is yet a third method that showed up. Again, trying to let home builders have a little bit of choice in this, a little bit of freedom of how do they want to approach this compliance. Do they want to hire third parties that can trade things off and maybe get their insulation levels down? Or do they want to just go with the cookbook method, the recipe, as I call it, in the IRC that just gives you the R values? Just do what it says. Well, those are all choices that builders get to make. The fourth option there, I didn't even block in. That's the tropical climate region. That also is pretty new, like 2018 code. And that is a very, very specific regions where you have a very different energy code. I'm not even going to talk about that because obviously tropical climate, I think we get the point, right? Most of us aren't living in the tropics. Lots more that could be discussed about all of those sections. The fifth one is new to the 2021, and it is simply says, okay, regardless of the compliance method you choose above, we still want more efficiency in buildings. And so the 2021 is going to mandate that you also do some more energy efficiency. And again, it doesn't matter, depending, you pick your original compliance method. And once you've got that satisfied, now you got to go look and say, I have to add something to it. I have to do more. And so this is essentially what it is it creates about 5% increased efficiency. So if you're using the energy rating option, you have to go 5 points lower. That's your additional requirement. Total building performance is a 5% decrease in energy costs. And then the prescriptive compliance simply adds some additional requirements that you get to choose from: high efficiency appliances, insulating pipes, bringing your ductwork inside the envelope. Again, it was just a way to kind of push energy efficiency even further, but maintaining the original compliance methods and simply adding an additional one. FYI, that is something in your governments that maybe are not all on board with the enhancements in energy. That may be something you see amended out, because the way it's added in like that, it makes it convenient for folks if they wanted to go, no, we're not going to accept that is our government code. So let's get into a little talk now about the prescriptive thermal envelope. Hold on, I got to do a clock check real quick. Make sure my time is right. Okay. So let's talk about the prescriptive thermal envelope. And as I kind of alluded to already, I called it a recipe. I maybe should have brought this slide in sooner. This is one of my favorite slides, though, when I'm talking about the IRC. Most of the IRC is just a cookbook full of recipes you can choose from. And if you follow the recipe, you won't give your family food poisoning. Right? You can figure out that analogy. If you follow the recipe for the structure of your home, it shouldn't collapse on your family. If you follow the recipe for energy compliance, you'll have sufficient energy and comfort and energy use in your building. It simply just says, do it like this and you're compliant. Now, very, very easy way to make dinner for your family, right? Just look up the recipe, but not necessarily the most flexible way either, is it? You follow the recipe, but if you don't follow the recipe, hey, no promise that this is going to taste as good as we promised it was going to taste. So if we look at that first recipe, the way the 2021, one subtle shift it has made is it starts out by talking about the assembly, like being a wall assembly, a ceiling assembly, a floor assembly, basement wall. You can see all the different columns, all the different titles for these columns. And what this is it is a U factor for that assembly. So it incorporates everything, the air space within the wall, that the air film on the actual face of the wall provides a small amount of R value, the gypsum board likely that's on the inside, a little bit of R value, the sheathing, and it allows someone to take that every piece of their assembly and determine an overall U factor and then comply with that. And so we're talking about continuous insulation, like a sweater. Well, do you wear a sweater in Florida? Probably not that many times of the year, right? So I'm going to be focusing in some of my examples to the colder climate zones, like where you might wear a sweater or a jacket, continuous insulation. So let's look at this example for these climate zones on the top here, or on the left, 4, 5, 6, 7, and 8 climate zones. And we can see that the minimum, or excuse me, the maximum U factor here is 0.45. Now, U factor is a reciprocal of R value. So you can easily calculate between R value and U factor by simply the reciprocal, dividing by 1, or either dividing by 1, or in this case, dividing by the U factor. So 1 divided by 0.045 is equivalent to about an R22. Now remember, that's not saying R22 cavity insulation. That's saying R22 of the entire assembly. So that's complete choice from the builder. If you're using an insulated vinyl siding, if you're using a 5/8 Type X gypsum on the walls versus a 1/2-inch gypsum, it's going to change your overall U factor. And you as the designer, you can say, here is my exact wall assembly of all the pieces together, and I meet this maximum U factor. There's a choice. But maybe that's too much work. You know, gosh, I don't know how to calculate that and how to figure out all these individual U factors. So next, the IRC says, fine, here's another recipe. Here's a recipe for just insulation R values. We'll make it really easy for you. You can see all the columns are essentially the same. Of course, this wood frame column now is referring specifically to wood frame, whereas the previous one for U factor, well, it could be steel framing, it could be wood framing, it could be any kind, because remember, you're going to calculate every single part, all the thermal bridges and the equivalents of those, and the whole thing to get your U factor. Here, it's dumbing it down to say, okay, this is for wood framed walls, and here's simply the insulation R values. This is another place there was a big increase from the 2018 to the 2021 code. So if I again show you just those 4 climate zones, or the climate zones 4 and up to 7 and 8. And let's compare that to what I just showed you with U factor. And you got 4 different choices in here. First, you could do cavity only insulation. And yes, I know that's R30. A lot of folks are probably going, did you say cavity insulation? I mean, there was times in the past that was our ceiling insulation levels. And in some climate zones, well, we're thinking, yeah, in your climate zone 0, it's still R30. So cavity only, R30, brainless, no problem. Build your wall, wood wall, however you want, 12-inch on center, 24-inch on center. Just fill it with R30 cavity. Could be a double framed 2x4 wall, like a double wall. The other option you have is to use R20 cavity with R5 continuous insulation. And that's what the CI stands for when you look at this table, continuous insulation. Another option right here in this recipe, you could use R13 cavity with an R10 continuous. And so what do we have here, my friends? 2x8 wall, or a double wall framing, or a 2x6 wall, or a 2x4 wall. So the energy code recipe and choices are designed around the different types of wood frame wall construction. So it correlates, it works, and it gives choice. How do you want to frame your wall? Pick that. And then this recipe will give you an option for that. And then the final option here, and this is again kind of new coming into your 2021, is the continuous only of R20. So that ignores any size, but build your wood frame wall however you want. We're not even going to worry about the cavity and what can fit inside of it. Just go full R20 on the outside. And notice the correlation here, right? Cavity only R20. But as I already said, we're getting R values in the sheathing and the air film and the interior wall finish. We're getting tiny little pieces of R value. So this R20 is comparable to the R22 that we saw when you did that U value option, where you're, or the U factor option, where you're going to look at the entire assembly. So we can see the correlation between all these different choices. Now, the shocking thing to a lot of folks, again, when we're coming into the 2021, that's going to kind of shake the industry up a little bit, is continuous exterior insulation, because that's not been common construction. You know, I started framing back in the late 90s, and I've never framed a house myself with continuous insulation. It's definitely a different kind of construction practice, driven a lot by new materials and new technologies and new building science that we better understand. So this is showing you a map of where mandatory prescriptive continuous insulation was previously required with the 2018 IRC. It would have been just climate zones 7 and 8. And with the 2021, well, we've now captured a whole lot more of the United States with climate zones 4, non-marine 4 and up. And so now we see this movement in the 2021 to mandatory continuous insulation. Now, mandatory, but mandatory after you've chosen the prescriptive path. Because remember, the prescriptive path is just a cookbook. Do these things and you're good. And so that's telling us, yes, once you've chosen that path for compliance, now you're looking at continuous insulation. Of course, there is always the option for R30 cavity, but what does that also do? It completely changes your construction method, right? From 2x6 and 2x4 walls to now either doing 2x8 studs, or what may be more likely the choice would be like a double stud construction. So either one of these, R30 cavity or continuous insulation, is definitely going to be a big learning curve and a big shift for the industry. And all I can say is this: we can see that this is certainly the direction that the codes are moving. But still, let me not say that this is so mandatory yet, because remember, part of the prescriptive choice is to use the total UA option, where you look at all the assemblies of the building. This is your ResCheck option. And so, like I was showing you before, kind of explained, but now I can show it to you. Here is your prescriptive R values. Just put all of these R values in all of these assemblies if you have them. But with ResCheck, it allows you to say, you know, I don't want to do all that wall insulation. Let's decrease the wall insulation. I'm not moving you down the column in the table. I'm showing a decrease in insulation in walls. But how are you going to offset that? By an increase of insulation, say, in your ceiling, or an increase of insulation in your wall R value. And the ResCheck software calculates all this for you. So this is continuous insulation, right? This is the movement we're seeing towards continuous insulation. And as I said, this is a little bit new. This changes how you do your window pan flashing and flashing. Do you set your windows back? Do you set them forward? How do you adjust your soffits and your overhang to get that standard size soffit? This is definitely not just something like putting in a better window. This certainly alters our normal construction practices a little bit. So let's look at something. This is just a very basic graphic, right, of a wall. Imagine that's just like your studs sitting there. We got the cold outside and it's all warm and toasty inside. And let's kind of look at everything that this wall has to do for us. So we need something to stop the studs from, we need something for buckling, backing, and bracing. And I'm going to talk about that in just a minute. Something for buckling, backing, and bracing. We need a water-resistive barrier, and that does generally need to be on the outside. Buckling, backing, and bracing, there's some variation. Water-resistive barrier needs to be on the outside to protect everything that we don't want to get wet. We need an air barrier, part of the energy codes, right? But an air barrier simply is there to stop the movement from outside to inside, or from inside to outside. That's it. So the air barrier could be on the outside, but you could also use an air barrier on the inside, perhaps. Your drywall could be your air barrier. Okay, it could go either place. And then, of course, your vapor control. And so vapor retarders are kind of the historical way that we've managed vapor. And vapor retarders were, in the past, we've had warm in winter side. So in the warm climates, you would put the vapor retarder on the outside. 2021 code really has developed in vapor control, and it's always going to be on the inside now, wherever you put your vapor retarder, if you do. But that's using a vapor retarder. And my title here says vapor control, because that's the point, right? We're trying to control water vapor. We don't want condensation. So there are other ways to do vapor control now. With insulation, you can do continuous exterior insulation as a form of vapor control. And now we're full circle back to the original feature that we're talking about that's a little new, is continuous exterior insulation for the sake of thermal protection, right? Keeping the heat from moving out for our own comfort and energy savings. But we see at the bottom, it's also now a method for vapor control. So wall sheathing. The first thing is buckling, right? If we have these studs loaded from the top and resisting on the foundation at the bottom, why don't we build decks out with 2x4 posts? Because the 2x4s will buckle. They don't have enough cross-sectional area. So first thing wall sheathing can do is keep your studs from buckling. But you don't have to use wall sheathing. The IRC actually has a way for you to do blocking if you want to keep the studs from buckling. But wall sheathing's the common choice. What's the next thing? Backing, right? Wall sheathing is there for backing for your different types of exterior coverings. So you may not need it on all of them. What if you're doing an anchored brick veneer, a big thick brick? Well, it has its own strength from wind loads hitting it and pulling away from it, positive and negative wind loads. So backing's not an issue. But what if you choose a vinyl siding? It's a thinner material. Well, now you are going to need a type of sheathing to provide a backing for those wind pressures based on your choice of exterior covering. And then, of course, bracing. That's one of the big subjects for wall sheathing, right? This does not look like a very well-built house, right? Someone didn't follow the recipe for structural stability in this house. What did they do? They've got parallel, they got horizontal running board sheathing on this. And so I don't want to live in that house. I'd rather live in this house. And look at this, the house isn't even there anymore. But what stayed up? The braced wall stayed up. And why? Because it's diagonal boards. So we have a triangle. And so the triangle creates that bracing. This is the old way of building. But then we started developing new products and new materials like black Celotex. How many of you have seen that in your remodel work? Or I even worked with some of that in the late 90s. Fiberboard sheathing, right? So once black Celotex came around, it was an easier, faster way to build. We can just plop up one big sheet, but we still had that lead-in bracing to create that bracing for the wall, to create that triangle. And then, of course, what's everyone using today, right? Wood structural panels. That could be plywood or OSB. Last time I tried to turn one of those panels into a parallelogram, I didn't have a lot of luck misshaping the shape, right? Because obviously it does a really great job of bracing because it stays in the shape of its plane. Now, these things that I've all mentioned, these are all just still in the recipe book. You can still do lead-in bracing. You can do wood structural panels. There's all kinds of recipes in the code for braced walls, for buckling. I said you could use blocking. Do you need backing for siding? Do you not need backing? That's all spelled out in your IRC cookbook. But aren't there other ways to cook a meal for your family? We don't all cook from the same cookbook, and we're all still eating, aren't we? So the IRC gives us this section, one to never forget, R104.11, alternative materials. And the sentence starts out saying the provisions of this code are not intended to prevent you from doing other things. It's like the cookbook saying, hey, look, we've offered you some recipes here, but we're not saying like you're gonna die if you don't follow our recipes. So what's another way you could make a meal for your family and know that they're going to be okay? They're not going to get food poisoning. Maybe from a chef, right? So what would be the analogy there? A design professional, like a cooking professional, educated and knowledgeable in coming up with unique and creative dishes. So you get an engineer, and an engineer could look to say this document, special design provisions for wind and seismic. Notice it says design provisions. It's not speaking to you and I. It's not a recipe for prescriptive, just, hey, man, just follow the rules. This is design provisions for the chef, for the engineer. What's another way that we might get food that we can feel confident is somewhat safe for us, right? Like Twinkies. Okay, I know maybe they're not the safest for us. I need maybe a better example. Maybe one of these new plant-based meats or something. Well, maybe that's not necessarily from a chef, is it? Or an engineer. This is more like a tested, like an FDA is going to come in and make sure your Beyond Meat or whatever is okay. And so this is where we get another way of compliance, which would be a tested product, right? Like this, for example, Thermoply. I knew of Thermoply back in the 90s. It's been a product that's been around forever. It's not a wood structural panel. It's not a lead embracing. It's not diagonal lumber sheathing. It's a proprietary product. So it gets tested like your Twinkies, if you will, to say, hey, is this going to give us the end performance we want? And so that's where we're back to maybe we can get this to our continuous exterior insulation, since we're putting it on this outside, and it's this new kind of thing that we're not all familiar with in construction yet, and definitely the direction the industry is going. Maybe it can also provide for us some buckling, backing, and bracing provisions. And maybe it's not wood structural panels. How would you verify that? How would you verify your Twinkies? Right? It's going to have to be tested. You're going to have to prove with evidence that, hey, this will do the job. So that section R411 for alternatives has a subsection about tests, simply saying, hey, tell us that this works. Give us the evidence that this is going to do the job of buckling, backing, and bracing. Now, one thing I'll mention real quick that I threw in here is this is what's coming for you in the 2024 IRC. Remember, the IRC is just model codes. We can all be a part of contributing ideas to it. Somebody came forward and said, I want to add another recipe to the IRC. And this was approved for the 2024 IRC as an appendix chapter. And I'm just briefly bringing it up to show you that these recipes aren't written in stone. We can all create new recipes to put in the code as options, or again, go with engineered designs or tested products. This is extended wall plate construction. And I'm just added it in this portion of the presentation because what does it speak to? Your wood structural panel and your foam plastic insulating sheathing together, right? As one piece, and looking at it as one design method. And this allows you a recipe now to simply use these, commodity products, if you will. So just another recipe coming for you in 2024. Maybe you have some recipes to propose for 2027. That's how these get created. People have to come up with them and propose them. All right, what else might be happening on these walls? The water-resistive barrier, right? I showed you that thing, and I took you through all the different things happening on our exterior wall. So water-resistive barriers used to be called weather-resistant barriers way back in the day. And actually, even in our recent history, it was still called a weather-resistant barrier. Let me take you back to one of my dork books here, my history books, This is from 1950. This is from the federal government, Forest Products Laboratory, Department of Agriculture. And look at this, condensation control in dwelling construction. In 1950, the federal government was trying to help research and provide guidance on how to do that. And here's a section from this book about sheathing paper. And notice what it says here. I love this. Sheathing paper, sometimes called breathing paper, between the sheathing and the finished siding has been customarily used to what? To reduce infiltration of cold air and to prevent the penetration of wind-driven rain. Weather barrier, right? Cold wind, cold rain. Weather, we associate wind and rain, precipitation, weather. So it's a weather-resistive barrier. And speaking specifically to sheathing paper, a product, not necessarily a performance. Now move forward in time to the 2000 IRC, and we still see the reference of sheathing paper, right? That doesn't sound like a lot of choice or options to me. That sounds like paper. Can you all imagine what paper looks like in your head? Yes. Well, the code's telling you paper. But notice what we're even seeing here. It wasn't even required. In 2000, you could build, depending on your siding material, without even having any weather-resistant sheathing paper at all. Now, move forward one code cycle to 2003, we still see the term weather-resistant sheathing paper, but now we're actually getting a statement telling us about where it needs to be installed. And in 2003, it was everywhere, except for those exceptions. But if you look at what it is, it's still referring to felt, to paper. Look at the title, sheathing paper. Paper, that's something in your mind's eye, and the code says that's what it has to be. Let's go all the way now to modern times, 2021, and no longer do we say water resist or weather resistive barrier. Now we are specific that this is all about water resistance. This is the water resistive barrier. And it's expanded in our choices. Look what it says. The water resistive barrier can be one of these 4 choices here. Choices lead to innovation, and it allows us to feel like we have a little more empowerment over how we want to build or how we want to have a home built for us. So what's the first choice, right? Good old tar paper, sheathing paper, just like what's in the picture, the basic simple commodity that's been around since, the 50s. What's the second choice? It references us to an ASTM standard. And that ASTM standard is essentially your sheet products, your house wrap or home wraps, and those are all trademarked terms, but you know what I'm saying, right? Your big sheet products that aren't an asphalt paper, but still somewhat similar, but proprietary. They can be made out of all kinds of things. People can be creative. You test it to a standard, and that's what makes sure all these creative ideas still are going to meet the same performance. Test standards promote freedom of innovation, and that's an odd to say test standards promote freedom of innovation. Most people think test standards restrict freedoms, but you got to shift your perspective. What's the third choice? The third choice is referencing an ASTM test for essentially testing windows, curtain walls, doors. So in case you came up with a water resistive barrier that you wanted to test it in the way that windows are tested. I'm not super familiar with that one, but guess what? It's another option. And then what's the fourth option? The fourth option is, hey, that's a pretty cool new idea. That's the way I word it. But what does it say? Other approved materials, other approved materials. That's the code saying, hey, that's a new idea, right? So what about the tape systems? There's manufacturers out there with wood structural panel systems that you can tape, and your water resistant barrier is built into it. This is an image from the sponsor of this today, and they have a product where the water resistant barrier is built into it. Hey, that's a new idea. How do we verify another new idea to perform the water resistant barrier function? Well, I already showed it to you, R401.11, saying, hey, you've got to simply validate that this works, and then the subsection for testing. Here's what this is saying in the code, guys. Anytime the code says or other approved methods, here's what I want you to look at it like. It's a now hiring sign. It's saying, hey, the code is simply saying out to the free public, out to everyone, say, hey, we're hiring for a position of water resistive barrier. We have this job that needs to be done. And we do not discriminate against all the different various applicants to do this job of water resistant barrier. And we're hiring more to do this job. You need to provide me with your resume and your work experience, right? Evidence that you can do the job that they're hiring for. And the code is looking for evidence. And this is where we would get compliance reports like ICCES reports or Dr. J. There's other providers out there that do code evaluation reports, a third party that will evaluate and basically provide that documentation to say, hey, look, I can do the job. Okay, cool. So maybe now water resistant barrier. Maybe we can integrate all of these different features. Maybe you can find one employee that can do multiple jobs for you. That might be easier for you as an employer. That's a choice that the IRC is making so readily available to you. Next one, let's do air barriers, right? Now, I was a framer back in the 90s and early 2000s. Well, I got into decks more in the 2000s, but this is me back in the late 90s in my 20s framing a house. And if I'd have seen air barrier written on the floor back then, I would have no idea what anyone was talking about. We didn't talk about air barriers, not in Colorado in the 90s when I was framing. But nowadays you see air barrier. This is, a superintendent on a job site writing for the trades professionals. Hey, you missed an air barrier here. Now, one of the reasons we never heard so much about air barriers, it wasn't so much of a mainstream topic, isn't because it wasn't in the code. The Model Energy Code 1983 talked about air barriers, had provisions for air barriers. But the thing was, it was a completely separate book. So it wasn't as easily available to all of us to access that information. It wasn't until the 2000 IRC that Chapter 11 of the residential code included the energy provisions directly in it. So they were basically in our face. And so you start to see more of a movement towards energy code compliance and energy code building, really starting around 2000 when it finally got mainstream enough to actually just put it in the one single book. And so this is a section from 2000. And what does it say? That the air leakage is about controlling the air leakage through the building thermal envelope, completely from one side to the other side. So it's all about occupant comfort, and it's all about heating and energy bills. It's all about don't lose the heat. It keeps you comfortable. Don't get the cold draft that makes you feel uncomfortable. Don't pay a bunch of money to heat your house just to have it bleed out your thermal envelope. It's all about going from outside to inside or inside to outside. And there's a reason I'm making that point. But look at this. I'm going to take you back in time again to 1931. Another document from the federal government, light frame house construction. My friends, 1931, we are almost 100 years ago. And what does it say here about building paper? I should circle the second sentence there. Will increase the warmth of the floor by preventing air infiltration. This is not a new subject. 1931, the government's trying to encourage us to be smart when we build because we don't want cold, drafty air coming into our house. So air barriers have been around a long time, weather-resistant barriers for rain and air. And that was our sheathing paper, was functioning as that. But of course, now here we are today. We have the IECC in Chapter 11 of the IRC, and we have a definition for air barrier. And it's silly, right? Materials put together to restrict the passage of air, what? Through the building thermal envelope. And then we have a definition for continuous air barrier, which it's kind of redundant. Not sure why we have that, but it just says it's air barriers that are a combination of materials, but it's all about preventing the air movement through the assembly. And then how do we know that we've done that? How do we know that we have blocked the air sufficiently from moving inside or outside, outside or inside? Well, this is something that's been slowly coming into the code, our blower door tests. It was optional before, and now under the 2021, it's mandatory. I believe that was actually the 18 shift that to be mandatory. But yes, no matter what your compliance method at this point, you will need to test the air leakage. But notice what it is. It's just a way to literally test the end result of the construction to say how much air actually gets through the building thermal envelope. It's a test that's done at the end after you've done everything, right? A blower door test. Many of you may be familiar with that. Depressurizes the house, and it has measuring units on there to determine, okay, how much air movement has run through here under a certain amount of depressurization. But how do you know what materials, how to build your assembly? What do you have to use? What's required? Well, the code doesn't give you a lot of that, right? It gives you a final test at the end to say, are you tight enough construction or not? Now that's under the IRC. I like to real quickly point people to this. This is the IECC commercial provisions, which would apply to buildings that are built under the IBC. So if you look at the full energy code and you look at this section, now this is again the commercial code section for air barriers, is different than for single family homes. Single family homes just say, do what you want, but you better pass the test at the end. But if you want, as a builder or a designer or specifier, you want to be a little more confident that you're going to work out at the end with the test, this section can be used as guidance to you to say, look, here under the IECC, there is an actual test requirement for the air permeability of these materials. So if you were looking for a proprietary, a different type of material that can function as your air barrier, you may want to compare to see, did they test that material for air? And then, of course, this code for commercial gives this huge list of materials saying we have deemed these as airtight, sufficiently airtight. So my point is, if you kind of follow some of this guidance as you select your materials for air barrier, it's going to help you have a better chance of passing that blower door test at the end. And the reason I keep bringing up through the assembly is because you could put your air barrier on the very outside of your wall sheathing, right? With those sheet type of products like this, there's various manufacturers on the market, and they seal these up, and they can be used as an air barrier at the very outside. But maybe that's not your style. Choices, my friend. Maybe you want to use an air barrier where your wall sheathing is actually your air barrier. Well, there's products like that on the market, like our sponsors of this presentation. There's other folks that make just an OSB. But when you see these taped sheathings, this is where they're going, well, hey, we're going to double up and let our sheathing function as our air barrier. That's a choice you get to make. Maybe you don't want to do that. Maybe you want your air barrier to be on the inside of your wall sheathing. No problem, right? The IRC is just saying pass the blower door test at the end. Keep your air changes per hour within the limits of these codes, and that'll depend on your climate zone. So there might be an example like this, where a builder is doing a spray foam against the inside to create their air barrier, and then they're completing their thermal insulation with a different type of insulation product. This is a choice. Or maybe you want to put your air barrier on the inside and make it your drywall skin. Because remember, it's all about testing air movement from the inside to the outside or vice versa. So you have some choice here. Now, a lot of folks had been doing their air barriers on the inside in the past. And then what would that mean? All of your electrical penetrations through that drywall, if you will, well, that's a hole for air. And so you can see here where they've spray foamed these electrical boxes to close off the holes. And if you look at the picture on the upper left, well, that sloppy drywall work looks like a big breach for air to move through. And if that's the level of the air barrier, well, we're going to need to seal that. You'll need to caulk and seal that. And then you can see here that spray foam kind of coming into the electrical box. Well, there's been some evolution on that. First, let me show you this table real quick. This is a second half of this table, and this is where the IRC, Chapter 11, gives you some guidance for air barrier installation. And kind of, you know, in the end, it's really about passing that test, but this is going to show you all the different ways that will really help to ensure that you pass that test. And if you notice here about electrical and phone boxes, what does it say? The air barrier shall be installed behind electrical and communication boxes. That would be if it was on the outside of the sheathing or the flash and bat, as they call it, the spray foam on the inside. In those cases, you don't have to seal your box. It's not part of your air barrier. What else does it say? Alternatively, air sealed boxes shall be installed. So this language is kind of speaking you to say, look, depending on where you choose to put this air barrier will result in different requirements in the code that to help you ultimately get to having that blower door test pass. Now, what's new for 2021 is this section, electrical and communication outlet boxes. This entire section's brand new for 2021. And now what that's going to require, notice that language, air sealed boxes. No more sealing it with spray foam that blows into the electrical box, takes up some of your space for conductor fill. Now it's telling us, for 2021, if you want to use the air barrier on the inside, you'll have to buy these specially tested air sealed boxes, tested in accordance with NEMA OS 4. This is just the cover of that standard. It's like an $86 standard, so I didn't buy it. I don't need to know it that bad. I know that if I was going to design a building with my air barrier on the inside under the 21 code now, I can't just do my own air sealing. I'll need to buy these special boxes. And that may be something that designers want to consider as they make all these choices. Every choice you make has an effect, a domino effect on something else. So back to our continuous exterior insulation, maybe it can double up for buckling, backing, bracing. Maybe it could also function as the water-resistive barrier. Maybe you can also integrate your air barrier into this. If you did, well, now you get out of buying those tested boxes. If you don't want to, well, you can see the result if there's going to be some other things you need to do. So all about choices. And then let's talk about the last thing, vapor management here. And then I'll wrap this up and we can get to the Q&A. I know I'm a little bit over my time, but I'm almost done here, guys. So vapor management. Now in the past, right, visqueen, plastic, polyethylene sheeting. Boy, did we do some bad stuff in the 2000s, turn of the century. Even the building code was not giving good advice. I mean, the building codes do the best they can to learn with the people as we are learning. Well, the idea of just throwing this up all over the walls created a bit of problem in that if we put that class 1 vapor retarder on one side of the wall without thinking about what is the vapor permeability of the material on the other side of the wall, we may find that we have vapor barriers, class 1 retarders on both sides. And now we have what's called a vapor sandwich. And one way or another, moisture finds its way into the walls. Either it's already there from construction or a little bit of air leakage brings some in. And a vapor sandwich, we have come to realize, is a really bad idea. We have to just accept that walls may get a little moist inside. The way the climate works and our need to control temperature in air, we have finally, the 2021 really pretty much says the message of, we know the walls might get wet. We don't want vapor sandwiches. We've got to let the walls dry one way or another. So in chapter 7 of the IRC, we're outside of the energy chapter, but boy, we're still really tied in with everything energy related, all the concepts of energy science. And so you can see this black bar. This is a brand new section, vapor retarders. I've got a 4-hour presentation just on vapor control. So this is now a very big subject, but I'm going to just bring it back to continuous insulation before I wrap this up. So we have this section talking about vapor retarders, and it's pointing us to a lot of different tables. And these are some new tables in the IRC. Here we get the different vapor retarder classes and the different types of material for each class. And each class has a different permeance. This is about how much water vapor can move through these products. Your plastic polyethylene is a class 1. Not much water vapor moves through. So it inhibits drying. And that's what creates those vapor sandwiches, if you will, where you're getting moisture damage inside because you're not drying. And then we get this other new table about your different vapor retarder. Wait, what does that word say? Options. Options, my friends. When you read the code and learn the code for yourself, you learn all the choices and options you have in it. When you wait for failed inspections or other people to tell you what they heard or what the inspector, you're not getting the full choice that the code gives you. So options are all throughout this book. Now, let's go back to those cold climates, right? Where we're going to wear jackets, where we want continuous exterior insulation. And we can see that we get we get 3 different kinds of choices. We can use a class 1, a class 2, or a class 3 vapor retarder. Now, a class 3 is like paint. If you look up there under the class, it's latex enamel paint. It's relatively vapor open, okay? But it still retards a certain amount. It's under 10 perms. So before I take you to the table that allows us to use a very vapor open interior vapor retarder in a cold climate, let me first show you what the table is about. So here's our wall. It's a cold climate. We're warm inside. We want to put a class 3 vapor retarder. No plastic. We don't want to risk the vapor sandwich. So we're just going to use a paint on the inside, a class 3 vapor retarder. That's going to do a really good thing for us. It's going to let that wall have the ability to dry to the inside. Okay, so at least, not sure what's on the outside here. Who knows? The code isn't getting into that question. It's simply letting us go, all right, we can now dry to the inside with this class 3, and we have less risk of that vapor sandwich and that real mold and mildew and decay starting inside the walls. But what does this also mean? Well, it also means more water vapor can move into the wall, right? We can move water vapor out to dry, but we also can move a lot more into the wall. And so that means we're going to have a higher relative humidity inside the wall with a class 3 versus a class 1, right? Well, it's cold outside, and we have this one sheet of maybe 7/16 or 9/32 or 9/16 wood structural panel sheathing. Maybe we got some OSB here, typical build. Well, the very back side of that wood structural panel is a very low surface. It's really cold because there's nothing warming it, right? You have the heat coming from the inside, but that heat is lost very quickly through the sheathing. So this is the recipe right there. A high relative humidity with a low surface temperature. We don't want 2 reds. That is a recipe for liquid water to create. Now, if it does create liquid water from condensation, okay, we do have the ability to dry, but we still want to try to reduce the creation of that condensation. So what we can do now, what this table allows, is if you use that class 3 interior vapor retarder, you can use a continuous exterior insulation. What's that going to do? It's now we got heat, right? Heat's moving through the house. We're losing heat, bad, bad. But that's the heat that keeps the inside of that sheathing warm. By putting insulation on the outside, we slow the heat moving away from that surface, right? So we have heat coming to the surface. That's good to keep it from condensing. And now we're going to retard how quickly that heat moves away from the surface. And what has that done? It's lowered that surface temperature. Now we're better off. We have a high relative humidity, but we also have a higher surface temperature. Oh, but what happens if we go with a bigger wall cavity? We want to increase our cavity insulation. Well, we have to think about that. We have now the same amount of resistance to the heat leaving the wall, but we've added a whole lot of resistance to the heat coming to the wall. So we have now just affected that temperature on the inside, and whoop, now we might be back to a low surface temperature again. And so what that table I'm going to show you will say is, if you increase that cavity insulation, slowing the heat coming to the back of the sheathing, now you got to increase your exterior. So we can also slow the heat leaving that surface, and we can get back to having high surface temperatures. I call this the battle of the dew point. We're trying to control that temperature between these two insulations. And so you can see here in the table that points to, you get the option. Here's climate zone 5, right? And we have a high relative humidity and a low surface temperature because we have a class 3 vapor retarder. So what are we going to do to fix that? Continuous insulation. And what that's going to do is increase that surface temperature by insulating our sheathing. Up until this time, we've always looked at insulation as keeping us, the humans, warm or keeping our energy bills low. This is where we're seeing insulation to literally keep the wall sheathing warm. It's not about us anymore. And so you can see it's an R5 over a 2x4 wall or an R7.5 over a 2x6 wall, that battle of the dew point. And you can see here in your colder climate zones, the colder it gets, the more it's pulling the heat away from that interior of our sheathing. And so we see we get an R10 continuous, an R15 continuous, right? So whereas we may have this for climate zone 5, and there's that certain amount of resistance to the heat being pulled away from the surface we're keeping warm. You go to climate zone 7, it's a lot colder. It's pulling that heat away a whole lot faster. So we have to increase that exterior continuous insulation. And so now we see how vapor control brings us full circle back to, hey, continuous insulation could also be a form of vapor control. And how much of this, based on choices you make, can you put into, say, killing two birds with one stone, as they say, right? But these are all what? Choices. Make your own choices. That's what really understanding the code empowers you guys to do. Thank you so much for letting me go through this brand new presentation, a little bit over time, and I imagine maybe there would be some questions. So let's certainly get to that, and thank you all for letting me share this.
Thanks, Glenn. That was a lot of information packed into your hour there. And of course, we did have a few questions. Some of these came up a little bit earlier, and we'll see whether or not some of the questions might be more appropriate for you, some might be more appropriate for Lee. But let's just start out with Joseph asked, is using a combination of R value and U value options for compliance allowable, or does it have to be one method or the other?
So it's going to be one method or the other. But remember, in R value is just the reciprocal of U factor. U factor is reciprocal of R value. So when you're doing the R value option, you're just looking at the R value of this and the R value of that, and it's of insulation materials. So you can only add like R value of continuous with R value of cavity, or maybe a spray foam with a fiberglass cavity, but it's a listed R value of a insulating material. When you go with the U value or the U factor approach, where you're looking at the whole assembly, that's where you can go beyond insulation materials, and you can actually pull in the fraction of a U factors that you get from, like I say, even just the air film on the wall does have an insulation value to it. So there really wouldn't be a need to merge the two.
Okay. Before I jump to the next question, I see that people had asked about will they be able to see this presentation. And yes, finehomebuilding.com/webinars, there will be a recording of this entire presentation and Q&A session within the next couple of days. So anything you guys want to recap or anything you missed, you can go back there and do that. Jim asked, you were talking about the air tightness tests for compliance, and his question was, how do you do air tightness tests on additions to old buildings? And I'm not quite sure exactly what he means by that. Maybe you have a good idea.
Yeah, when you get into, if you're doing an addition, then only the addition needs to comply with the new provisions, and you would not be required to blow or door test the entire house again.
Okay. Lee, let's see. Somebody was asking, can we assume the building code specified insulation values do not have a dew point concern? Is there a tool or software we can use to calculate the dew point when we're using different insulation values?
So there is a very basic website that I use just to kind of teach the concept of dew point. It's like dewpointcalc.org. And it simply allows you to bring in different temperatures. It's not really related to our value of insulation. I do believe there is a organization, the Air Bear, or there's an industry organization that I unfortunately can't remember right now, that I believe has a really good online calculation tool for determining what the dew point of different materials are based on the temperatures. But I don't really have that off the top of my mind to recommend. I apologize.
Okay. Lee, maybe this is a question you can help out with. Somebody was asking, they said, one of the challenges with continuous insulation is getting clear information about detailing, transitions, window and door flashing, and that sort of thing. Is that, I imagine that's something that's taken into consideration when designing and introducing a product that's an all-in-one solution.
Yeah, that can be tricky from time to time, but the biggest challenge is when you get above an inch of continuous insulation. If you're able to maintain about an inch of continuous insulation and you have enough density in the foam or a high enough PSI to the board, then you don't really have to change a lot of the things that you're doing, like bucking around windows and going that route. You do just have to understand how to weatherproof in different ways, as opposed to, so many people are used to doing a building wrap and just cutting the corners and dropping it over. You just have to kind of work through how the taping works on that. But, at Ox, we do a lot of training with the contractors. So if there's a contractor new to our product line, we'll actually do a pre-construction meeting, and we'll have someone out on the job site when they start installing it, just to make sure that they're up to speed with that. But yeah, there are a few tricks and challenges, but we try to help out our customers as much as possible and kind of working through those details. And my background as an architect, I do a lot of work with architects and helping them provide the details in written form or in drawings prior to getting to construction as well, which is helpful.
Okay, thanks. Now, does the perm rating of the exterior insulation, sheathing, and WRV have an effect on when Class 3 vapor retarder is allowed on the inside?
So this is where there still needs to be a little development that I expect to see in the future with the code. Right now, when it comes to the use of using that Class 3 vapor retarder on the inside in a cold climates and using the continuous exterior insulation on the outside, it was written under the assumption that is essentially a vapor closed, or a Class 1, a very non-vapor permeable kind of a foam insulation. Now, of course, we know that there's rock wool insulation, there's fiberboard insulation, there's a number of continuous insulation products on the market, and probably more to come. Again, that's the beauty of innovation, that are vapor open and would change some of these effects of terms of drying and which way are we now allowed to dry. So generally speaking, no, it's not really, it's kind of, the code is sort of just assuming you're relatively vapor closed on that outside. Now, that said, in that table for Class 3, there is another option I didn't get into with this because this is a continuous insulation. I was wrapping it all around that subject, but using a ventilated cladding. Using a ventilated cladding on the outside helps to create more vapor drive through to the outside. And the goal there is to get you drying in both directions. But right now, it's only speaking to either ventilated cladding to get you that outward drying, or continuous insulative sheathing and or insulation, and assuming it's essentially very vapor closed, class 1.
John asked, continuous insulation in table R702.73. The continuous insulation thickness for zone 6-7 is greater than required on the prescriptive thickness. Can you explain why?
Okay, so this question comes up all the time. The combinations are not quite the same, and the reason is, here's basically the reason. First reason is chapter 7 of the IRC is developed completely separate and independent from chapter 11. Chapter 11 being energy. Like, there's a lot of professionals, a lot of folks in the industry very interested in energy code, and they attend and participate and contribute to the development of energy code. Chapter 7 is for vapor management, for water vapor, building science, wall assemblies. It's not created by the same folks. It's not created in the same hearings. And unfortunately, because of that, you do get some disconnect between the two. What I simply say is this: they are two totally different subjects. Chapter 11, continuous insulation, is all about the thermal comfort of the occupant and energy savings, the cost of energy. It's all about moving heat energy through the assembly and reducing that, again, for bills and for occupant comfort. Chapter 7, continuous insulation, has nothing to do with occupant comfort. It's all about keeping the inside of the sheathing above dew point temperature, or using the ventilated cladding. So you just have to look at that in two different ways. One way is using insulative sheathing. I'm going to use this recipe to satisfy vapor management. Now let me look at this recipe, and how am I going to manage thermal control? Right? And maybe it's like making a dinner for your family, and you might have the same ingredient in the main course as you have in the side dish, but the recipe for the main course is different than the recipe for the side dish, even though it uses the same ingredient. I don't know. I like analogies. Okay. I do expect further development of this into the future, because this is a question that comes up all the time, is this disconnect between thermal and vapor control.
All right. Robert asks, this is a question for you, Lee, recommendations for products compatible with OX that will provide a drainage plane between your sheathing products and the siding.
Well, our sheathing actually is 98% drainable, and so it is a drainage plane. Usually what the siding manufacturers require is just a small gap between whatever that siding is and ours. And so if you do some type of a furring strip or hat channel or something like that to get the finished material away from our product line, then it will drain very, very well. So that's all that's needed, is just a space between the two products.
Okay. Yeah. And I mean, I know in Fine Home Building over the years, we've been focusing a lot more and more on rain screen detail. So yeah, there are a lot of options there, and that almost is sort of irrelevant to what the sheeting material is underneath, right? It's just creating that space.
Right. As long as that sheeting material is drainable, and that's what we've focused on ours, is just to make sure we have a base for them to work off of to create that drainage plane. Yeah.
Okay. And so Glenn, this might talk to your vapor sandwich topic a little bit. Someone asked about closed cell foam interior and continuous foam exterior. What are your thoughts on that? Or either one of you?
Closed cell foam interior and continuous foam exterior insulation with a rain screen. I mean, so rain screen is good for drainage, but also helps for drying, for relieving vapor pressure through that assembly. You've got your continuous on the outside. So that, let's see. So yeah, I
guess the worry is that having a sandwich of sheathing, a water sensitive material in between. I mean, in the case of the Ox product, the insulation's on the inside of the sheathing. Is that correctly? So that would be irrelevant, or?
Well, your sheathing, no, your sheathing's actually against the stud that you're installing there. So the foam would be exterior of that.
Okay.
Yeah, I don't see an issue with what they're trying to do. As long as you're working through the right dew points and understanding how that assembly works. And obviously this varies based on your climate zones and different options there. So there's a lot more, I guess, to dive into than just talking about those. But closed cell foam interior and continuous exterior insulation with a rain screen is great. But what other pieces are there? I guess would be my question.
Yeah.
Someone asked, should a township official accept a passing ResCheck report regardless of insulation values?
Well, so you can trade off all the different insulation. So, I mean, the ResCheck software, I mean, it's, you're going to be limited to practicality, how much you can add in one place to reduce in the other place. But there is no like ultimate minimum that you can't go below for the ResCheck option. And when you get into the performance option and the energy rating option, there is like a baseline building thermal envelope that you can't go below. You can't trade off too much. We want to create that robust thermal envelope because it's there forever. But under the ResCheck way, you don't get that minimum for insulation values, but you do for windows, because you can trade off like higher insulation for lower performing windows to a point. There is a section that provides an absolute minimum saying you can't put windows in worse than this. So that would apply for your U factor for your fenestrations, like your windows, but not for your insulation values, specifically using the ResCheck method.
Okay.
But the nature of the math is still going to, ultimately, it'd be hard to do the math, for like no insulation in the walls. Like, I don't know, it'd be tough to get that math to work out with insulation elsewhere.
Okay. Lee, can you talk about, is this something you've dealt with some of the architects, dealing with continuous insulation at deck ledgers attached to a house?
Yeah, so there's a couple options there. I mean, I've actually had engineers kind of go through and basically re-engineer their ledger, which in essence they're just adding additional attachment points to be able to attach through continuous insulation. Ideally, that's what you'd want to do, is just to continue your insulation down, attach the ledger board to the outside of the insulation with additional attachment points. And the engineer can calculate that for you. So instead of, you're attaching it, I don't know, 12 inches on center, you're then attaching at 8 inches on center or whatever that might be. You just do it a little bit tighter attachment pattern to make up the difference of the cantilevering effect of the insulation.
Okay, that makes sense.
I mean, you can cut out the insulation and do that route, but you lose the whole idea of continuous insulation in that regard. And then there's a lot of flashing details, which could get a little hairy.
Did you have a comment on that, Glenn? Or no?
I was just going to say, if you like the prescriptive, you do have to be careful. The prescriptive design methods for attaching a ledger in section 507 does not allow you to use lag screws over foam. But it would allow you to go up to 1 inch of foam with a bolt, with a through bolt. Okay. But beyond 1 inch, with only a through bolt, nothing to accommodate lag screws, through bolt, maximum 1 inch. And then otherwise, as Lee said, you're into specific engineering.
Yeah.
And I think there's also a couple of proprietary solutions for that. Like, what is it, the main deck ledger or something like that? It's like a bracket that actually has an interior and exterior component for a small penetration to get past difficult claddings and insulation details on the outside. Yeah,
tested product. Like I say, we got your chef and you got your Twinkies, right? So engineered design or tested products. But yeah, thanks for mentioning tested product. Always another way to approach your validation that you will resist the loads.
Okay. Yeah. So we're getting closer. We're getting about 20 minutes past. I'm going to ask one more question. I know we had a few others, but I think it's about time to wrap things up. But one attendee said they have a house with existing 3/4 inch board insulation on the exterior, and closed cell foam was needed to meet code in an existing 2x4 wall when they were doing work on the place in Massachusetts. And the HERS rater it says the insulation company felt that this was fine. Are there any comments on that? Or
yeah, I mean, the closed cell foam is essentially like your class 1 vapor retarder. So that's where we're not needing to get that continuous on the outside. The point of that continuous on the outside and maintaining that high surface temperature is all about being able to go to a class 3 paint and eliminate any of that vapor retarding from the inside. But if you're going with a closed cell foam, you're kind of taking care of that problem by not raising the relative humidity. You're not allowing that humidity to come through and get to that sheathing. So, I mean, it seems like that, like I say, like Lee said before, there's a lot of details that go into this to really getting these assemblies right, but that doesn't sound like anything too shocking or unrealistic.
Same here. Yeah, I would agree.
So before we go, Lee, if anybody that didn't get their questions answered have questions about construction details regarding continuous insulation, what sort of resources do you have to answer people's concerns?
So we have a number of different installation guides on our website based on the products that you have available. And then we leave ourselves open we have a whole technical team that can kind of walk through and help with those, architects and engineers and all types and builders that are part of our staff that can kind of go through and help work through any questions that anyone might have in that situation. So really a quick look at some of the details that we have on our online. And if there's nothing there, feel free to reach out to me and I can kind of walk you through any questions on that.
All right, great. Thanks. Well, again, just want to remind everybody that this recording of this session will be on finehomebuilding.com/webinars sometime next week. And that's where you can also see all of our past webinars and sign up for any new ones. Thank you so much, Glenn and Lee. And thanks again to Ox Engineered Products for sponsoring this presentation. And I hope you guys all have a good night.
Thanks. Take care, guys.
Thank you.